Hi guys, today we're going to be talking about or a good chunk of chapter 2, which is going to discuss atoms, molecules, and ions. We're going to talk a bit about how to interpret the different symbols that we use when we refer to atoms. So what do the different numbers mean? What does that tell us about the atom, its properties, for example? We're going to talk about the different masses that are given on the periodic table and how those are obtained. And then we're going to talk about, again, some of the properties within the periodic table, as well as how to name given compounds. Okay, so when I look at an element symbol, so elements are going to be anything found on the periodic table, there are some numbers that you need to be able to know what they represent and how you can use them. So whenever I look at the symbol of an element, the first thing that's going to jump out at me is going to be the actual atomic symbol. That's what's going to be found on the periodic table. So for example, here I have C for carbon. And then written to the left of it, I have two numbers. The first is a superscript, in this case 12, and the second is going to be a subscript, in this case 6. The subscript is going to represent, that's the number that they use to actually order the elements on the periodic table. You'll notice that it starts with 1 and goes up from left to right. So carbon is the 6th element on the periodic table, and what this 6 tells me is either the number of protons, which is what usually people associate it with, but this is also equal to, so protons, or it also tells me the number of electrons. And the reason for this is that every single element on the periodic table is actually neutral in charge. So if I'm going to have a neutral atom and I have 6 protons, where protons are positive, then I must have another 6 electrons, which are negative, to cancel out that charge. So the atomic number tells me both the number of protons and the number of electrons. So this number is the same for every single atom of a given element. If I were to change this by adding another proton, so if I were to go, for example, from a 6 to 7 here, 6 protons to 7, I would no longer be a carbon atom. I would now be a nitrogen atom, and I would have all the properties of nitrogen. This subscript over here on the left, this represents the atomic mass for that element. So not the weighted atomic mass, which is what we're going to see on the periodic table, but for this actual member, this atom of carbon, I'm saying that its atomic mass is 12. And the atomic mass tells me two things. It tells me that the sum of my protons and my neutrons, so that's what the atomic mass is. So given that I know the number of protons from the atomic number, I can then find out my number of neutrons using the atomic mass. Okay, so neutrons are going to be neutral, so I don't need to worry about canceling out any charges here. So again, the mass number, that's going to be the superscript, and that's going to represent the sum of the protons and the neutrons. Sometimes you'll see an element written like this. So for example, calcium with a +2 or some kind of plus or minus and a number up to as a superscript on the right. This number is not telling you anything about the protons and the electrons. Well, I guess it could tell you, the protons or the neutrons, but instead this is talking about the charge on the ion. So this isn't an element anymore, this is now an ion, and specifically it's an ion with a charge of +2, so it's given up 2 electrons. Alright, isotopes, so atoms can have variations within them. They can vary in the atomic mass. So since the protons have to be the same, that means the only thing that can be different is the number of neutrons. So carbon, for example, can exist in 4 different isotopes, though most of them are very rare. So I can have C11, C12, C13, and C14. However, if you look at the atomic mass of carbon on the periodic table, it's something around 12.011. So from that, I can tell that most of the carbon is going to be C12, and that's accurate. So approximately 99% of all the carbon found in nature is carbon 12. So this number that's found on the periodic table is what's known as a weighted average. So the atomic weight that's actually found on the periodic table is actually what's known as the element's atomic weight, and this takes into account all of the isotopes that are found in nature. Okay, so it includes all possible isotopes weighted by their relative abundances. And the way that I always tell people to think about this is it's very similar to the way that we calculate your grades over at Taylor. So at Taylor, 50% of your grade is your major grade, so that's your tests, your lab reports, whatever. 35% of your grade are minor, and 10 or 15% are other. So if you had gotten a 78 on all of your major grades, but you did pretty good on your quizzes, so you had a 94 quiz average and you did all of your homework, the way that you would calculate your grade in the class is very similar to the way that you would calculate that the atomic mass. So what you would do is you would convert these percentages to a decimal, multiply them by the number that they represent, and then add all of those numbers up to get your final grade. So what you would end up doing is doing 78 times 0.50 for 50%, 94 times 0.35 for 35% of your grade being a 94, and then 0.15 times 100 for your other grades. So you would calculate each of these numbers individually and then add them up to get your final grade. So let me do that. Okay, so I went ahead and did those calculations. So 78 times 0.5 gave me 39, 94 times 0.35 gave me 32.9, and 15% of 100 or 0.15 times 100 gave me 15. So then I take all these numbers, so 39 plus 32.9 plus 15, and that gives me my average in the class of an 86.9. So the same thing is true for atomic weights. So let's go ahead and try an example of that. Okay, so here I have another problem. In this case, I'm looking at 3 different isotopes of magnesium. So remembering that means they have the same number of protons, but where they differ is their number of neutrons. So the first one is 78% of all magnesium, and that's 24. The next is 10% of all magnesium, and that's 25. And 11% of all magnesium, which is 26. So again, I'm going to convert these percentages into decimals. So this would be 0.7899 times 24. This would be 0.1 times 25. And this would be 0.1101 times 26, or whatever masses they give me. In this case, they just give me the isotopes. So I'm going to calculate what each of those is, add them up, and that will give me the mass of magnesium weighted by their percent abundances.